Hey Calculus, we are going to keep working on limits and introduce a couple of properties. So example number 1, is there a limit at x is equal to 1? So let's put our vertical line through the x value of 1. Okay, so let's trace the graph. From the left, we're coming in at a y value of 2. From the right, always trace the graph, we're coming in at a y value of 2. So absolutely, is there a y value at x is equal to 1? Yes. Why or why not? Because the left limit is equal to the right limit. It's a great date. You're meeting in the same place. Correct calculus notation. The limit as x approaches 1 with a little minus sign up there of our function is equal to 2. And then the correct calculus notation for the right limit, the limit as x approaches 1 with a little plus sign up there of our function is equal to 2. And then finally we can say, so the limit as x approaches plain old 1 of our function is equal to, 2. Okay, let's go to part B. Is there a limit at x is equal to 2? So let's put our vertical line now through the x value of 2. And again, always trace the graph. Coming from the left, we're coming in at a y value of 5. Coming from the right, we're coming in at a y value of 5. So once again, the left and the rights are the same. You're meeting in the same place. It's a great date. So, answer is yes. So the limit as x approaches 2 from the left of our function is equal to 5. And the limit as x approaches 2 from the right of our function is also 5. So that allows us to say that the limit as x approaches 2 of our function is 5. Okay, on to example number 3. Is there a limit at x is equal to 3? Gotta get my highlighter here. Okay, so let's put our vertical line through our x value of 3. Now let's trace the graph. Coming from the left, we're coming in at a y value of 10. Coming from the right, we're coming in at a y value of 8. So in this case, our left and right limits are different. It's a bad date. You're meeting in different places. There is no limit. So we are going to say no. All right, the limit as x approaches 3 from the left of our function is equal to 10. And that is not equal to our right limit. The limit as x approaches 3 from the right of our function is equal to 8. So in that case, we have to say that the limit as x approaches 3 of our function d n e. All right, a couple things to point out here. This right here, when there's a step in the graph, and it's also sometimes called a jump, that is another kind of discontinuity. All right, when your left and right limits are different, there is a step or a jump in the graph. That is called a step or a jump discontinuity. Just like we know this one right here at 1, there's a hole there, a removable discontinuity. So those are two kinds of discontinuities that you need to be aware of. A step and a hole. Okay, let's go to example number 2. Okay, f of 2. This is asking you for the y value at 2. All right, so when x is 2, what is the y value? So let's go over to 2. Let's go up to the graph. It looks like right here, hey, the point 25 is definitely on that graph. There is no hole there. So f of 2, everyone, is equal to 5. 5 is on the graph. All right, part B. Is there a limit as x approaches 2? Right here. So let's put our vertical line through 2 and always trace the graph when you're looking for a limit. All right, from the left, we're coming in at 5, and from the right, we're coming in at 5. So the left and rights are the same. The limit as x approaches 2 is 5. All right, and hey, whenever your y value is the same as the limit, then it is continuous right there at 2. There is no discontinuity. Okay, can a limit exist if there is a hole? Absolutely. Yes. Your example was right here at 1. There's a hole there, but there's still a limit. The left and the rights are the same. It's still a great date. You're meeting in the same place. Think of it as a pothole. You can hold hands over a pothole. Okay, part D, can a limit exist if there is a jump or a step in the graph? And that is no, absolutely not, because your left and rights will be different. That is what happened up at 3. There's a step there because the left limit is different than the right limit. Okay, example number 3. We're just going to practice finding limits algebraically. If you remember, the first thing we ask ourselves is, can we do direct substitution? Can we plug in 4 here and here? And we can't, because when I plug in 4 on the bottom, 4 minus 4 gives me 0. Now, the second thing you check for is, do you have in the indeterminate form, 0 over 0? So if I plug in 4 on top, 3 times 4 squared, well, 4 squared is 16. 16 times 3 is 48. 48 minus 48 is 0 over 0. That is an indeterminate form, and that tells us that there is probably a limit there. So that is your clue now to factor and cancel so that we can plug in the 4. So we have the limit as x approaches 4. We're going to leave our denominator alone, but we can factor the numerator. The first thing we can do here is we can pull out a 3. 3 goes into 3 and 3 goes into 48. So when we pull out a common factor, we put it out front and we rewrite that binomial. When you're pulling out common factors, you're just dividing. If I take 3x squared and divide it by 3, I'm left with x squared right here. Bring down the same sign, and if I divide 48 by 3, I get 16. And you can always check by distributing. 3 times x squared gets me back to 3x squared. 3 times 16 gets me back to 48. Now, I still can't cancel anything, but I can continue to factor. This is a difference of perfect squares. Okay? So I can factor that. So the limit as x approaches 4, that 3 comes down. It's still part of your answer. Don't forget about it. But I can put x squared minus 16 into 2 perfect square binomials. So the square root of x squared is x and x. My first terms have to be x. The square root of 16 is 4, so my last terms have to be 4. And the signs have to be opposites. All right, so that allows me to cancel here. So now I'm left with the limit as x approaches 4 of what's left, 3, times x plus 4, don't forget that 3, now I can do direct substitution. All right, I can plug in 4. 3 times 4 plus 4, 3 times 8, my limit is 24. Okay, let's go ahead and do this example. Now we have the same process. Can I do direct substitution? No. I end up with 0 on the bottom. If I plug in 3 on top, I do get 0 over 0. So now I go ahead and factor and cancel. I'm going to use synthetic division to factor this guy. So my coefficients are 1x cubed minus 8x squared plus 22x minus 21. My value that makes my denominator go to 0 is 3, so the 3 goes out front. All right, now we go to work. Bring down the 1. 1 times 3 is 3. Now I add negative 8 plus 3 is negative 5. Now I multiply. Negative 5 times 3 is negative 15. All right, now I add right here. That's going to give me a positive 7. Then I multiply 7 times 3, gives me a positive 21, and then I get my 0. All right, so now make sure you rewrite your synthetic division correctly. So we have the limit as x approaches 3. My denominator stays the same, but I'm factoring my numerator into this right here times this. Now remember, this up here, you guys, is the root, but I need to write its factor. Remember, the factor is right here. It is x minus 3. So that goes right here, x minus 3, and this right here comes down right here. And it's 1x squared minus 5x plus 7. You need both of these factors. This times this is equivalent to this. So don't forget this one. All right, because you need it to cancel out this guy. All right, so now we have the limit as x approaches 3 of what's left, x squared minus 5x plus 7, and now we can plug in 3, direct substitution. So 3 squared minus 5 times 3 plus 7, 9 minus 15 plus 7. I'm seeing positive 1, right? Okay, there we go.